Use implicit differentiation to determine dy dx given the equation x to the sixth plus y cubed equals cosine y. So this function looks a little bit different and trickier because we have this trig function. But it doesn't make the problem really any different at all. We are going to use implicit differentiation because it's not really possible here to get the variable y by itself. So we just go term by term and differentiate as we would normally. So x to the sixth will differentiate into 6x to the fifth using the power rule. There's no dy dx attached to this because it is not a function of y. Next, we have this piece, y cubed. And this is a function of y, so we're treating it as an outer function, which means we use the chain rule. The chain rule says take the derivative of the outer function, so 3y squared, multiplied by the derivative of the inside function. Well, the inside function isn't known, so we just call it dy dx. Then we come over to this part with cosine. Again, it's cosine of an outer function, and that tells me to invoke the chain rule. The chain rule for cosine says take the derivative of cosine, which is negative sine. Leave the inside portion alone, but then multiply by the derivative of the inside portion, which is dy dx. At this point, we need to get dy dx by itself, so bring everything with dy dx to one side. I would have then, let's say, sine y dy dx plus 3y squared dy dx, and I've just brought the term on the right over by adding it. Now I'm subtracting the 6x to the fifth to the other side. I can factor out dy dx from the two terms on the left-hand side. And that leaves me the ability to just divide that remaining term over. So I have dy dx equals negative 6x to the fifth over sine y plus 3y squared.